For the remaining lessons in this unit of study on electric potential and electric potential energy, we're going to focus on gaining practice by working through a few problems selected off of previous AP exams. So here's one from the AP Level B exam from the year 1987. This is problem number 2. And we're given a charged object with a magnitude of 3 microcoulombs and a mass of 0.0025 kilograms. And there's a point P located 30 centimeters away. And so we're asked, what's the electric potential at this point P? How much work would have to be done to bring a second charged object of 1 microcoulomb to the position P? What's the electrostatic force that object 1 and object 2 exert on one another? What's the magnitude and direction of the electric field at a point midway between the two objects? And then we're told that objects 1 and objects 2 are released from rest. Because they're both positive, they repel each other in opposite directions, and we have to find the speed of object number 1 once they get very, very far apart. Okay, so if you'd like to, you can locate this document, print out your own copy of it, and probably also want to grab a calculator to work through this problem. So if you need to hit pause and take a moment to get those resources, feel free, and then continue on with the rest of the lesson. So let's take this all one step at a time. The electric potential, well, we don't have to go through the full derivation. We know we can work, we can say the electric potential at point P minus the electric potential infinitely far away. We can work with this expression as equal to negative the integral as we'd go on a path from infinitely far away to the point P of the electric field dot dr. And point P is just at a distance of r away. Well, the end result is we're going to find that the electric potential at point P is simply equal to kq over r. So this is going to be 9 times 10 to the 9th times 3 times 10 to the negative 6th divided by 0.3. I suppose I should put in the units and double check. This is 9 times 10 to the 9th Newton meter squared per coulomb squared. 3 times 10 to the negative 6 is coulombs, and 0.3 is meters. So one of the meters cancels, one of the coulombs cancels. We're left with Newton meters per coulomb. That's joules per coulomb, and hey, that's volts. Okay, so 10 to the negative 6 and 10 to the 9th just gives us 10 to the 3rd. 3 times 9 gives us 27. So we've got 27,000 divided by 0.3. 27,000 divided by 3 would be 9,000. So 27,000 divided by 0.3 would be 90,000. There we have it. V is equal to 90,000 volts. Now there's this second object whose mass is the same as the mass of object number 1, but its charge is 1/3 as much. They're both positively charged. How much work was done to bring the second object from infinitely far away to point 2? So we say that change in potential energy is equal to negative the work done by the electrostatic force. But this question is asking how much work was done by some external agent or by some external force. So the work done is the same thing as the change in potential energy. Now when object 2 was infinitely far away, the potential energy of the system is equal to 0. So really change in potential energy is just the potential energy when the two objects are at a distance of 30 centimeters minus the potential energy when they're infinitely far away, but that's 0. So the work is the change in potential energy, but the change in potential energy is just the potential energy associated with them being 30 centimeters apart. And as we know, this is calculated with the formula K, Q1, Q2 divided by R. But we already calculated what K times Q1 over R is. That's 90,000 volts. So really, we're just saying the work is the potential energy is equal to the charge that was moved to point P times the electric potential at point P. So this is just 1 times 10 to the negative 6th coulombs multiplied by 90,000 joules per coulomb. Now 90,000 is the same thing as 9 times 10 to the 4th. So 10 to the negative 6th and 10 to the 4th gives us 10 to the negative 2. 9 times 1. Okay, so 9 times 10 to the negative 2 is probably better just stated as 0.09. And of course the coulombs cancel out. We're talking about 0.9 joules. Yeah, that's the amount of work that was done to bring that object from infinitely far away to point P. All right, just to be clear. All right, part C. What's the magnitude of the electrostatic force that the two objects exert on one another at this distance? So let's make sure we're considering Newton's third law here. This is the force that object 2 exerts onto object 1. This is the force that object 1 exerts onto object number 2. And we note that both of those vectors are drawn exactly the same length, because Newton's third law tells us that all forces come in equal and opposite pairs. The way we calculate that force is from Coulomb's law. So it's K Q1 Q2 over R squared, 9 times 10 to the 9th, times 3 times 10 to the negative 6th, times 1 times 10 to the negative 6th, divided by 0.3 squared. Check the units. Newton meter squared per coulomb squared times coulombs times another coulomb divided by meters squared. So the meters cancel out, coulombs cancel out. Yeah, we're just left with newtons. We're trying to solve for force after all. So 10 to the negative 6 and 10 to the negative 6 is 10 to the negative 12th. 10 to the negative 12th with 10 to the 9th gives us 10 to the negative 3rd. 3 times 9 gives us 27. 0.03 squared is 0.09. Or, I'm sorry, 0.3 squared is 0.09. So if we move this over 2 places and call it 9, then we also have to here get rid of 2 powers of 10. So instead of 10 to the negative 3rd, this is 10 to the negative 1st. So this is just 2.7 divided by 9. So that's 0.3 newtons. What are the magnitude and direction of the overall electric field at the midpoint? So charge 1 produces an electric field vector that points to the right, and charge 2 produces an electric field vector 1/3 as large that points to the left. The reason I know it's 1/3 as large, the distances are the same, right? That's d over 2. Oops. That's d over 2, or in other words, 15 centimeters. Same distance here, also 15 centimeters, but of course the charge is 1/3 as much. So, right, the electric field is going to be 1/3 as much. So really we can just put this together and say, if this is called E naught, then the net electric field, this is going to be 1/3 E naught, then the net electric field is just going to be 2/3 of E naught. And what do I mean by E naught? That's the electric field that was produced by object number 1. So that's 9 times 10 to the 9th times 3 times 10 to the negative 6th divided by 0.3 squared. We know the units are going to work out to give us newtons per coulomb. Okay, so if you want to go through that exercise of convincing yourself the units cancel, fine, I'll leave that out for here. So 10 to the 9th and 10 to the negative 6 is 10 to the 3rd. 9 times 3 is 27. well, but then divided by 3 again, I guess we're back to 9, times 2 gives us 18. Then we need to divide that by 0.09. So we move that 2 places. So that means we have to move this 2 places. So this is 1800 divided by 9, which I guess would be 200, huh? So 200 newtons per coulomb. The two objects are released, and they move apart due to the electrostatic force between them. No other forces act on the objects. There's no air resistance. We're ignoring the force of gravity. What's the speed of object number 1 once the two get very far apart? So at this point, there's a potential energy, as we found earlier, equal to .09 joules. That's at a separation of 30 centimeters. Once they get very far apart, then the potential energy is 0. So the change in potential energy is 0.09 joules. Well, what does that get converted into, right? Energy can't be created or destroyed, so these have equal amounts of force in opposite directions, and because they're the same mass, that means they're going to accelerate equally in opposite directions, which means over time they'll always have the same speed as one another in opposite directions. And that's what the potential energy is converted into, is energy of motion. So the increase in kinetic energy comes from the decrease in potential energy. 1/2 m1 v1 squared, so that's for the 3 microcoulomb charge, plus 1/2 m2 v2 squared has to equal the change in potential energy, which we know we're going to substitute as 0.09 joules, but as always we'll save the numbers for last. But the masses of these two objects are equal, so I don't really need subscripts 1 and 2. And likewise, just because of the law of conservation of momentum, we know that v1 has to equal v2, so I don't really need subscripts there either. And try to convince you what I mean by applying law of conservation of momentum. So before they're released, both objects were initially at rest, so the total momentum of the system is equal to 0. Now when they go flying away, individually they each have some magnitude momentum, but the momentum for the object moving to the left is negative, and the object moving to the right is positive. And if the initial momentum is 0, then the final momentum has to be 0. And so if they each have equal mass, then they must each be moving with equal speeds in opposite directions. So really then we just have 1/2 mv squared plus 1/2 mv squared for a total of mv squared is equal to delta U. So this quantity V is equal to the change in potential energy divided by the mass of either one of the particles square root. So this is the square root of 0.09 joules divided by 0.0025 kilogram. Remember, a joule is a Newton meter, and a Newton is a kilogram meter per second squared. So kilograms cancel out, and we've got meters per second squared multiplied by meters, so meters squared per second squared, but we're taking the square root, and so yeah, in the end we're going to get meters per second. What do we get? 0.09 divided by 0.0025. Take the square root of that, and we get 6 meters per second. Okay, not a bad problem. Let's move on to the next.